It turns out the C++ standard library already provides several predefined function objects for basic arithmetic, equality, relational, and logical operations. To use these predefined function objects, you need to include functional. The arithmetic function objects include negate, which simply returns the negative of its parameter. It's the only unary operator of the arithmetic function objects. Then we have plus, minus, multiplies, divides, and modulus, which have the obvious meanings. These are all binary function objects. For equality and inequality, here on slide 17, we have equal to, not equal to, less, greater, less equal, greater, equal. And we also have logical not, logical and or. Logical not is a unary operator. All of these others are binary operators. Now, in these notations for these predefined function operators, the parenthesis in the end here indicates a constructor call for creating one of these function objects. The parentheses is not itself, in this example that I highlighted, a call of the plus function. Let's take a look at some examples. Here on slide 18, we're basically setting up a couple of vectors, v1 and v2. And then on slide 19, we have some code making use of those vectors, as well as some empty decks, d1, d2, and d3. Okay, so let's take a look at slide 18 first. v1 is a vector of int, and we've got 10 int values initially within v1. And this copy algorithm is going to display those values separated with spaces to the screen. v2, you'll notice, is a copy of v1, but we're going to use random shuffle to make sure that the order of the values in v2 is vanishingly unlikely to be the same as the order of values in v1. So in order to do a random shuffle on a sequence container that supports bidirectional iterators, we specify the begin and end iterators, and random shuffle does its thing. So when we display v2 using copy, we get the same values out but in a different order. Now let me display that output. Alright, so the first line of output that we have here on slide 20 are the elements of v1, and the second line of output are potentially the elements of v2 after it has had a random shuffle performed on its elements. Okay, so in the second half of our program here on slide 19, I have three empty decks of ints, d1, d2, d3, and into d1 I'm going to use this back inserter to insert values reading from v1 and negating each one of those values. Alright, so this notation, negate, angle bracket, int, close angle bracket, and then open close parenthesis, creates a negate function object for ints. And that negate function object is going to be applied first to the initial element of v1, then to the second element of v1, and so forth, with the results being put into d1. When I use copy to display d1, values separated with spaces, sure enough I see that the red output here on slide 20 is simply the negative of the values in the first line of output. Now, the second transform here on slide 19, this is the version of transform that takes two input sequences V1 provides the first sequence of values, and V2 provides the second sequence of values. And as before, transform is assuming that there are at least as many elements in V2 as there are in V1 in order for this transform algorithm to work. This time I'm creating a back inserter into D2 so that the result of this transform goes into D2. And because I have two input sequences, I have to use some kind of binary function. Here I am creating one of the predefined plus of int function objects. And so if I look at the contents of D2 coming from this copy, what I see is that D2 contains the sum of the respective elements of V1 and V2. So 4 plus 0 gives me a 4, 7 plus 7 gives me a 14, 1 plus 3 gives me a 4, etc. And then in the final transform here on slide 19, once again I'm using V1 for my first input sequence, V2 to provide my second input sequence. Here I'm putting values into D3, and I'm invoking this constructor to create for myself a greater int function object. Now what greater int is going to do is to compare the current value coming from V1 with its corresponding value from V2 to see whether the value from V1 is greater than the value from V2. If so, that will produce a true, but if we store true into a deck of ints, it's going to store as a 1. Likewise, a false is going to store as a 0. So let's see what's happening here in the output from this black copy algorithm. 4 is greater than 0, so I get a 1. 7 is not greater than a 7, so I get a 0. 1 is not greater than 3, 3 is not greater than 8, 4 is not greater than 4, so I get 3 more zeros. Then 9 is greater than 8, 8 is greater than 5, so I get 2 1s, and so forth. Okay, so those were a couple of quick illustrations of some of the standard function objects that are defined for you as part of the library. Now the final stuff here in Lecture 14 shows how to use something called bind to combine together various operations to accomplish more complex calculations in algorithms. And bind is pretty powerful, but it's also a pain in the neck to learn and a pain in the neck to read. So since nowadays we have these nice things called lambdas, I don't really want to spend time talking about bind, and I'm not going to expect you to know anything about bind. Okay, so that takes care of Lecture 14.